So the story starts with the fact that trading nowadays can be executed on the millisecond level or nanosecond level, 10 to the power of minus 9. Now, if you look at the price evolution throughout the day, so at 9:30 when most of the trading starts, at 4 everybody goes home, there is a lot of information on the price variation which is happening throughout the day. And when we were talking about the daily risk measures, what we usually did, we took the closing prices for the current day. However, we're not taking into account all the information, and the realized volatility allows us to do so. So in order to get from our usual discrete time kind of stories of the financial econometrics, we are going to think about our return process, R, the log return process, which continuously evolves over time. And again, this is a plausible assumption these days. And why? Because the high frequency trading is allowed these days. So we are talking the log of the price at period t minus the log of the price at the previous period, if you like, where here t minus 1 is not necessarily the day, it could be previous second. So I would assume that for simplicity, our return process has no conditional mean. So the idea here is that we do not start to think about what kind of form does this epsilon take. We rather say, okay, we would go into the theory of subordinated stochastic processes. So if you look empirically at the data, and if you look at the return, so you have, for example, your prices at 9 a.m., first minute, first second. Then you have your price at 9 a.m., first minute, second, and so on and so forth. Now, if you look at the corresponding return for 9 a.m., first minute, second, and then the third second, which would be the log price difference. If you look at those returns at the really high frequency data, the high frequency level, conditional basically on their variance, you could think about them as a subordinated stochastic process. Now, what does it mean, subordinated? That means nothing else as that this process is indexed by time. And time here would be, let's say, time I, that would be the real valued process. So we would say that time evolution is, so our time is now, can be evaluated at any continuous point I, so at any millinanosecond, and that would be a real valued process which kind of directs our stochastic process epsilon t. Now, a stochastic process which is subordinated by time, we would say that we can assume that epsilon t would be normally distributed with zero mean, sigma squared, I don't know, some sigma squared x times t. Now, you might be wondering about the normality assumption, but again, think about it as a really high frequency increments, and think about the following property. So in order to proceed with our stochastic theory processes, we need to assume that the time changes are independent from price increments. So the intuitive idea would be that if you are not very familiar with stochastic processes, that there is this time guy. The time just continuously evolves over time. And it just goes on and on and on and kind of subordinates or directs the stochastic process of the log prices. Now, what you kind of say that, okay, the time has changed and the price increments just evolved in a random manner, so stochastically. And they have evolved continuously, and in the continuous world, you would say that, okay, the time basically governs the variance of your process. Another way of how to look at this, if you look at the return indexed by I, given the time change, time increment, Ti minus Ti minus 1, again, here I denotes a very teeny tiny time increment, nanosecond increment. Then in the stochastic world, we could say that conditional on the time increment, our returns would be marginally, so to say, normally distributed, where the variance of the stochastic process is indexed by time. So marginally, over a small time increment, our return is a normal mixture. It is symmetric, but it is fat-tailed. So note here the volatility of this process, or the variance of this process, evolves over time and is directed by the time increment. So this guy allows for the fat tails. The normality assumption tells you that you're going to get over a small time increment symmetric distribution of the return process. So it is often observed, if you look at this really millisecond, really very tiny, teeny tiny increments of the returns, if you look at the returns at the ultra high frequency, they, so to say, possess a martingale property. So, once again, what is happening right now? So now I'm treating my time to be continuous. And then I can have Ti and Ti minus 1. They are just the 2 points on the continuous time evolution. Now this increment in time basically governs the volatility of my log returns. Again, log returns, they are assumed to be now continuously evolving over time. And what you're trying to do, you're trying to characterize how do they look like. And then if you look at them empirically, the ultra high frequency returns, you often observe that these RTs, they possess a martingale property. What is a martingale? Just to remind you, so you need two properties. So the first one is that the absolute value of the return is finite, expected value. And then the most important property is that if you look at the forecast for your next continuous time process and continuous time return at time t, given the some information on the continuous time evolution return process, where s is somewhere between 0 and t, then your best kind of thing you could do, you could just take the last available return value. So that would be two martingale properties, and indeed you often see that. So you often see that there is nothing in there. So again, marginally, the returns would be some kind of symmetric but fat tail distributions, where the volatility is stochastic, meaning that it evolves over time as indexed by time increment. Now, how does the return distribution differs from another distribution? Let's say in usual financial econometrics, we would say, okay, we compare our return distribution, our demeaned return distribution with the white noise property. So we were looking whether our ARMA specification is allowed, so to say. Now, kind of similar story is valid in the continuous time processes. And now the whole idea of the financial econometrics is to try to understand how this distribution, the marginal over small time increments continuous time distribution of the returns, differs from a Wiener process. Now, your Wiener process is kind of your normal error term or white noise in discrete time. The Wiener process, sometimes called Brownian motion. Now, what is a Wiener process? That is a continuous time process which starts at 0. Then, if you look at the increments over time, so you see how does your Wiener process W changed from t plus u compared to the t. So u is your price increment. So you see how the Wiener process changed over some small period of time. So those guys, their Wiener process increments, they are independent of the previous sample path of the Wiener process. So whatever happens before, then you look at the future kind of increment of the Wiener process, and it's independent of the previous continuous time evolution. Very, very roughly, that means that you kind of have this kind of random noise, so to say. So the evolution of the Wiener process happens independently of the history. So you have kind of IID property. Now, another property of the Wiener process is that the Wiener process has Gaussian increments. So in particular, if you look at those increments, the evolution of the Wiener process, where you just look u kind of nanoseconds ahead, that would be normally distributed, and the variance would be governed by exactly the time increments. So you see the similarity here. And of course I forgot that the Wiener process is continuous in t. So now, this Wiener process is our kind of ZT, our IID normal random variable. In the continuous time, this all has all these special names. This is now a continuous time stochastic process, and it satisfies these properties, most importantly that your Wiener process increments do not depend on the previous evolution, and the increments of the Wiener process would be normally distributed. Again, here we're talking about the increments over a couple of seconds, couple of nanoseconds, couple of milliseconds. So really 2 points in time which are very close to each other. Now, indeed, if you look at the high frequency data and you look at your log returns, which are computed over, let's say, some milliseconds, then indeed you would see normal kind of shape, but a stochastic volatility process in the sense that the variance is indexed by time. And the next step basically is to describe, so how does the stochastic variance of our log return process evolves over time exactly. Okay, and then you need to remind yourself what is another little thing, which is an etostochastic integral. So the concept which allows us to marry our return over some very small price increment and a continuous Wiener process. So those two guys, they come together in a stochastic integral, which says, okay, basically what you need to do, you take your Brownian motion, your Wiener process, and then you add on some stochastic volatility on top of that. And basically by changing the variance of the Brownian motion, you arrive into your continuous time return process. So what is an etostochastic integral? You take your return, continuous time, and then you integrate from 0 to t some sigma s, and I'll talk about this in a second, with respect to the Wiener process. Now, by definition of the integral, what is it you're doing? So our 0 to t, this is our continuous time. Now you consider pi n, which would be the sequence of the time partitions. So you take the millisecond ti minus 1, ti, ti plus 1, and then you look at your log return evolution over these little time partitions. So what do you do then? You say that, okay, if we let our kind of number of partitions go to infinity, and then we consider the limit of the following sum. So we sum our variance evolution over this tiny time partitions, and then we say, okay, you look at the variance of your process with respect to the change in the Wiener process. Okay, so this is horrible handwriting. So what is written there? Again, let's look at this lim sum. You take your Wiener process increment, which you know is independent of the past history and is Gaussian. So by definition of the integral, what are you doing? If this is your return evolution, then you see how much did that involve over time with respect to your random normal noise, if you like. Okay, so what are the ingredients of the etostochastic integral? So first, you take these time partitions. You take little increments in time, and you allow a lot of those teeny tiny increments. And then you start to sum up your random increment times the okay, let's call it just sigma for now. So now this sigma that has some sort of properties, and this is where your French might be useful. So we say that our sigma is a special process. This process had Cadillac sample path. What is Cadillac? So continue à droite, limite à gauche. In human language, that means that it is right continuous with left limits. So you allow the volatility of the process to evolve continuously over time, such that it continues from the right and has the limit from the left, right? So this is the continuous time process language for saying that your sigma is not going to be -5. Now, these guys, they are normal. And what's their variance? Their variance is exactly the difference of the time increment, the teeny tiny small number. Now, this Wiener process is by definition a martingale process. Why? The martingale process, you need to, of course, restrict the time evolution, but it's not relevant for this context, most importantly because you remember we had this property number 2 of the Wiener process, that the increments of the Brownian motion, they're independent of the previous realization. So now you kind of say, okay, under which conditions can I say that my continuous time log return process is also a martingale? Because we have here our martingale increments, and then your idea would be to bound this guy to be finite in certain sense. And that would basically allow you to develop a theory which describes how the continuous time log return process evolves. So, what do we do in order to make sense of the martingale property which we observe in the real data? So, RT would be a martingale if you bound the volatility. So you take your integrated variance, you say that that should be finite, and if that guy is finite, then you have that your RT is a martingale. Okay. Now, this sigma squared, which is evolution of your stochastic volatility over time continuously, that is called spot variance. And basically, you can define spot variance of any continuous time process. Now, why am I talking about all of that? So if you say that your sigma sample path and your Brownian motion, your Wiener process, they are independent, then you have the super cool result of the continuous time modeling, that if you kind of condition on the integrated variance of the process, so this is called integrated variance. Then you say that marginally over some small price increments, your log return would be normally distributed with a known variance. Okay, so what just happened? We said, okay, we would like to go away from our previous modeling of the log return process, and we say that this guy RT evolves continuously over time. Let's go through the whole story once again. So you have your return process continuously evolving over time, so your continuous log return process. We assume that there is no conditional mean for simplicity of notation. Then you would say what you often observe over really some small time increment over a millisecond, over a nanosecond, that those returns, log returns on high frequency data, they would possess some symmetric kind of looking normal distribution with some fat tails. And then you say, okay, what if we allow our stochastic volatility here to be indexed by time, and this guy is also continuous, and then what do we do about that? So very often you observe in the data the martingale property of the log returns. There is no structure in there, time series structure, so given some previous high frequency log return, the best thing you can do in predicting it is to taking the last value you see, and it's finite. And then you say, okay, the best thing I can do when I'm describing some sort of continuous time process, I could think about the Wiener process and then try to modify the Wiener process such that it satisfies the properties of my continuous time return. So the Wiener process has independent increments which are Gaussian. And what we don't like about this Gaussian increments, we don't like the variance of this process. So we would like to modify the Wiener process such that here we have some stochastic volatility. How are we going to do that? Well, we are going to use the Ito stochastic integral, which explicitly allows us to do so. So you integrate the continuous time evolving sigma process, which is a Cadillac sample path process. And that's nothing else as just saying, okay, there is some stochastic volatility in my Wiener process. And then the new terminology for you here would be the spot variance. That's the evolution of the continuous time variance, and the integrated variance when you take the whole variance of this continuous time process up to time t. Whenever you see a stochastic integral, if you're not familiar with stochastic calculus, do not be afraid. This is nothing else, it's just the limit of the sum of the following sum, where you look at a lot of different time partitions. So this is your Gaussian increment of the Wiener process, and this is some sigma which evolves over time. So basically you're trying to understand how does this guy have evolved over time from 0 to t. And for that you integrate those over from 0 to t, or you just look at the limit of the following sums.